Okay, let's continue from where we stopped last time, and let me first quickly summarize what we have done so far. So we have written down that the fields in the interacting theory we can express as the following. In terms of fields in the interacting picture, so phi I, and you have to sandwich between these operators. Okay, and where I had okay, I think I wrote down the expression of u earlier. Why it's not going back? Yeah. So here is the expression of u and u dagger. Oops. Okay, and we saw that u is unitary, so u dagger u is 1. Okay, and then we had also written down the differential equation that u obeys. Okay, where we had defined what Hi is, and that is just the interacting part of the Hamiltonian written using phi i's and pi i's, and where you take the Hamiltonian interacting part of the Hamiltonian and make the replacement, phi going to phi I and pi going to pi I. That is what we had found earlier. Okay. And our task is now to find a solution for this differential equation together with the boundary condition that u t0 is 1. Okay, because from the definition it's clear that u t naught is 1. Okay, now that's what we are going to do in this lecture. We are going to find the solution. Okay, and the difficulty arises from the fact that these are operators which do not commute with each other. In fact, HI's at different times also do not commute. See, HI's are made out of fields, and these fields do not commute, okay, unless they are at equal times. So in general, HI's at different times will not commute. Maybe I should write. Okay, there is some problem. So this is not true in general, right? Only when you are looking at equal time commutation relations, then the fields commute, but HI's when constructed this way, because they are fields, and if you are looking at HI with fields at time t and HI at fields at different times, okay, then they will not commute. Okay, so this is the source of difficulty in finding a solution to this. So we will go in steps so that things become easier. So to begin with, if these were not operators, okay, these were ordinary functions, then the solution is easy. Okay, then you would expect that u would have u of t will be like this. That's what you would expect, right? But given that these are operators which do not commute, we will have to do more things. Now, if HI's were commuting, if U's and HI's, all these things were commuting, they, let's say even when they were operators, okay, or think of them as matrices, and but they were commuting, then we can still easily find a solution. So these are all imagined scenarios. If H and U were all commuting, then the solution would be this. Let me so just to have a red flag, I am saying that these are imagined scenarios, so these are not the real, this is not the real situation. Okay, maybe what I will do is I will write in red for a while so that there is no issue. Or maybe not. Okay, so let's see whether indeed this would be a solution if these were all commuting. So first I should tell you what it means to write in this form if H is an operator. So the meaning of this expression is as follows. So this you should this is formally defined as the following. So 1 minus I T naught to T H I T prime dt prime plus minus I square over 2 factorial, and then you have T naught to T and so forth. Okay, that's the meaning of this exponential. That's the this expression. The second line is what is meant by writing this exponential. Okay, and let's verify that indeed this is the case. Maybe I will leave it as an exercise to, or maybe I can do it. Not difficult. So let's check that indeed what I am saying is true. So let's take that expression here, this one, and differentiate it with respect to time t, with respect to this t. So when it acts on the first term, it gives you 0. When it acts on the second term, it gives you hi of t. Okay, so you can think of it like this. So you do the integral, okay, and you get whatever. So let's say h tilde represents the integral of hi, okay, and then you put the upper limit, so that will give you hi of t, and the lower limit will give you t naught. Now when you differentiate this, you get back again hi of t, okay, because this is the integral of hi, so differentiating it will give you again hi. So it's clear that if I were to differentiate this term, I am going to get hi of t, okay, and the similar situation is here. There are two factors, okay, so you use the chain rule, okay, and you will generate two terms, okay, and then you can again just find the derivative easily. So let me give you what you will get. So check that you get the following. So the first term will give you minus I times hi of t. The second term will give you minus I whole square over 2 factorial that you already had, and then as I said, we will get hi of t from the first integral, and then you have the second integral left with you. Okay, I have changed the name of the variable. Instead of calling t prime and t double prime, I am calling t1 and t2. So let's go back and check. So this one I have taken care of. I am working on this one. So first I take derivative of this term times this one, and then this one times the derivative of this, and using the argument which I gave for this first term, you see that this will just give you hi of t times this integral plus this integral times hi of t. Okay, so that's what I have written here. Plus, then you get minus I over n, minus I to the n over n factorial, and then you will have hi of t, and then instead of one such factor you will have n minus 1 factors. Okay, so if this n minus 1 is telling you that there are such n minus 1 factors, and then you will have other terms. Just like you had two terms here, you will have in total n minus 1 terms. Okay, just like the above. Now you can pull out hi of t from each of the terms. So I do that. So I pull out minus I hi of t, and I get the following. So this one gives me 1, this one gives me, so I have pulled out minus I have a 2 factorial here. Okay, and what, this is also pulled out. Okay, and these two are same, right? You can change the dummy variables, and these two are identically the same. So there is a factor of 2 coming from here, which cancels this 2, but I will keep it. So I get a factor of 2 from these two terms because they are identical. And then you have integral t0 to t hi of t1 dt1. Okay, so and so forth. And this term you get minus I power n minus 1 over n factorial. Okay, and then you get here, I pulled out this, so you have n minus 1 such factors. Okay, I am writing this term, and you will get n minus 1. No, sorry, n. You will get n. They are total n terms, not n minus 1 terms. Okay, so that's what you will get. And now I can cancel this 2 with this 2 factorial here, and this n, when I cancel with n factorial, it will give me n minus 1 factorial. Let me write it cleanly. So this will become, let me write the coefficient of this one. It will become minus I to the n minus 1 over n minus 1 factorial, and this will have n minus 1 such factors, right. So you see that this is just an exponential again, okay, and which is what we said the answer is. So I mean, this is our beginning thing. I think where I gave the answer. Yeah, this is the answer I gave, this expression, and you see we have recovered this one. So this is again u. So I get minus I hi of t and then u of t0 to t, right. So clearly this is a solution provided hi is commute, okay. But as I said, this is not the true situation. So let me put a red color to warn. This is true only when all the operators are commuting. Okay. But nevertheless, whatever we have done will be useful in finding the true solution. So let's go to our real situation, and this is our real situation. So what do we have? We have T0 to T delta T minus I hi T u of T0 to T. Okay, that's the one we want to solve with the boundary condition that equal to 1. Now there is a nice way of doing it. It's just some algebra that I should do. So what I do is I integrate on both sides, okay, and first I will change the arguments here. So instead of t I will write t1. You can write it, there is no problem, okay. And now I do an integral over t1 from t0 to t. So I do this t0 to t dt1 del u over del t1, okay, and this gives me t0 to t and dt1, maybe I can write it to the right side. Okay, so all I have done is I have integrated on both sides, okay. Now when you integrate the left hand side, you just get u of doing the indefinite integral gives you u of t1 t0, then you put the upper and lower limits, you get u of t t0 minus u of t0 t0, which is 1, okay, and I can take that 1 to the right hand side. So minus 1 becomes a plus 1, and then you have this term. Okay. So this is fine, but I still have u here, okay. So I do not have a solution yet, but what I can do is I can take the left hand side and put t equal to t1, okay, and substitute in here. So what I'm saying is, let's take this expression and substitute in here. So what do I get? I get 1 plus T naught to T minus I, this piece is Hi of T1. But now the first argument is T1, so I should put T1 here, okay, and T1 here. So let me do it. So what is this? This is 1 plus integral T naught to T1 minus I Hi, okay. Here it should be dummy variable, so I should write T2 U of okay. Let's check whether everything is correct. So maybe it will help to write this for U of T1 T naught. This will be 1 plus T naught to T1, so I am replacing T by T1 in here, minus I Hi. Now this was a dummy variable, integration variable, so that I change, and you see this is what I have put in here, okay. So up to here this was the same, and when I got U, I replaced 1 plus this and this, correct, okay. So now what I will do is I will take this one and again make this replacement, but this time I want T2, so this becomes T2, this is T2, this dummy variable I should change to T3, okay, and then substitute in here. So if I do that, I get the following. Okay, I am always careful that I am never changing the order in which these operators appear, because as I said, things do not commute and I cannot change the order. So I have to be careful. Now we substitute this thing. I should write D2, I should write DT1. And when you substitute this, you get 1 plus T naught to T2 Hi T3, okay, and U T3 T naught, okay, and you have a DT3, okay. So this is how it will go. So you keep substituting for U this expression. Okay. So what you get eventually is the following. Okay, I'm not sure everything is okay. Yeah, this and this one. Okay, so what you eventually get is this. Let me just copy from my notebook. 1 plus minus I dt1 Hi of t1, that's what we had. Let's go back. This piece, so when you are multiplying this with 1, okay, that's what you get. And then you have other term minus I t naught to t dt1 Hi of t1 and t naught to t1 dt2 Hi of t2. Okay, so you should read it like this, because here you have to do the t2 integral first and the limits go from t naught to t1, but t1 is the integration variable here, right? So now you are doing integral over t1, so this has to be maintained. And then let me write one more term here. It was minus I square, now minus I cube, t naught to t dt1 hi of t1 integral t0 to t1 dt2 hi of t2 integral t0 to t2 dt3 hi of t3, and you continue like this. Okay. So I think I said that already several times that you cannot interchange the order in which hi appear in the integrals, okay, because in general fields do not commute. You know this, that this is not true in general. So this is, they do not commute in general, okay, and of course they commute if t prime and t are same. So that's the equal time commutation relation, but here as you see hi's are at different times. For example, this one has hi at a time, I mean the time argument of hi is always smaller than the time argument of hi here, right, because here the integration limit of t2 goes from t0 to t1. So the maximum value t2 takes is t1, okay, and then you are doing integral over t1. So t1, the t2 always remains below t1. So hi of t2 and hi of t1, they are always at different time arguments, okay. They do not commute in general, and similarly here, okay, and that is why we have to be careful with the order in which we have written things, okay. So good, then what? Yeah. So I have already said something here which, so you see the hi's appear in a particular time order. So if you look at this term, for example, here t3 goes from t0 to t2, right. So the maximum value t3 takes is t2. Then t2 goes from t0 to t1. So the maximum value t2 takes is t1, and then t1 runs from t0 to t. So this is the hi's, these three hi's, they are ordered in a particular time, in a particular order. So to the right you have the one with the lowest time, then the next lowest time, and then the highest time, okay. So it is running this way. So you always have the operator hi at lowest time to the right, and then you successively go towards left, ending up with the highest time, okay. So I will define a time ordered product of these hi's then, okay. So I will write, maybe I'll write here and then go to the previous sheet. So we have hi of ti1, hi of ti2, in. We are going to have for the nth term n such h's, okay. And suppose that ti tj n is the smallest one, okay. So this is the smallest time, followed by this one, and so forth, and then eventually, okay. So suppose this is how these different times are related. So this is the smallest one, this is the next one, this is the next one. Then I define a time order product of these h operators, hi of ti1, ti2, hi of tin is this. So you should take the smallest one and put it first, and so I am saying that this is the smallest one, so this comes first, then hi of tjn minus 1, and so forth, and then you end up with hi of tj1. Okay. So this is what is called time order product of these operators. Okay. So what I can see is that this expression I can write using the new definition that I have written, 1 plus minus I, there is nothing to be done here. The second term is minus I square T naught to T dt1, T naught to T1 dt2, and these two HIs I can write using the time order product. Okay, this is exactly the same thing. It's naturally ordered here. Now I have just written the same thing explicitly. Now if you were to interchange HI T1 and HI T2, so if you put this way and that way, it's still the same, because time ordering operator knows that it has to put the smallest one first and the second one should be the one with the larger time. So no matter which way you put these H's, the time ordering operator will always make this happen. So it will always put in this correct order. Okay. So that's the advantage. And maybe I can write this one more term, T naught to T dt1, T naught to T1 dt2, and T naught to T2 dt3. Okay. And then you have time order product of HI of T1, HI of T2, and HI of T3. Okay. And you can interchange the order within the T and nothing changes for the reasons I explained above. So that's what I have got. Okay, that's good, but you see, we were expecting something like an exponential here, right? So where was it? Yeah, this is what we had written. Okay, and here the difference from what we have right now in our calculation is that the integration limits are all going to T. Okay, and then you have all these nice 1 over 2 factorial and 1 over 3 factorial which produce an exponential. And what we have, sorry, I think I said opposite. So we had seen here that in this context you get 1 over n factorials at each order, at each power, and then the integration limits were going from T naught to T for all the variables. Okay, and you get a nice exponential. But what we have now is the integration limits are going from T naught to T1, T naught to T, or in this case T naught to T2, then T naught to T1, then T naught to T. So that's one difference. Upper limits are not all T, and you also do not have n factorials in the denominators. Okay, so that is the difference we are seeing, but a small exercise can show us that we can bring n factorials in the denominators and put all the upper limits of integration to be the same as T. So that's what we are going to do. So here is a, let me write it as an exercise, though I am going to solve it, but let's put on the heading exercise. So what we have here is, let's look at this term, the second one. So you have integral over T1 and T2, and T2 goes from T naught to T1 and T1 goes from T naught to T. Okay, so let's look at that space. So you have T1, you have T2, okay, and from T naught to some value T, both the, I'm just constructing this. So consider a square whose lengths are T minus T naught, whose length is T minus T naught. Okay, so it's a square. Now the full volume here in this T1 T2 space, okay, is this. right? That's the full volume. But I can divide it into two parts like this. So the division is in the following way. So if you are in this region, okay, then for any value of t1, let's say this t1, for any value of t1, t2 goes from t0. So here t2 takes a value t0. So t2 goes from t0 to maximum to this, right? So when you are doing integration over t2, this is how you are integrating. Okay, and what is this line? This diagonal line is t1 equal to t2 line. Okay, so you see that in this region, when you are integrating, your t2 is always below t1, right? Because this is the line t2 is equal to t1, and any point below this line in this region is t2 less than t1. So this diagonal line, okay, naturally divides this square into two regions. In one region, one variable is always less than the other, and in the other region, it's just reversed. Okay, so that's the division that has happened in this. But you see that the sum of these two regions is the full region, okay, which says integral dt2 t0 to t1, okay, and then of course you integrate over the full t1, that's this region, okay, plus now t1 goes from t0 to here, okay, and this is t1 equal to t2 line. So the maximum value t1 takes here is t2, and then you integrate over, okay, so dt2 t2 then goes from 0 to t. So this is t0 to t, sorry, not 0, this, okay. And how much is that? This is the full volume. Okay, so that is good. Now, what I have got in this expression here is one of those regions, right? This is one of the regions which I have written, but it comes with a time order product of these two h. So let's then see. So what I do is I write here hi of t1, hi of t2 time order product, and here also a time order product of hi of t2, hi of t1. So I'm just writing this. Okay, in fact, let me write the same thing. And here also. So I'm integrating over the same quantity in all the three, right? So this is then allowed. Now you see that this one and this one, they are identical, because I can change the dummy variable t1 to t2. So this will become dt2, and this one will become t1. So this is exactly the same as here, and here that does not doesn't bother, because it becomes hi of t2 and hi of t1, but I can write it the other way around exactly like this, because the time ordering operator will take care of everything. Okay, so you see that the left hand side is just both the terms on the left hand side are same. Okay, so you see that this implies that integral t0 to t dt1, integral t0 to t, I am writing this one, dt2, here I forgot t of hi of t1, hi of t2 is equal to 2 times of this object. Okay, so integral t0 to t1 dt2 and time order product hi t1 hi t2. this one is dt1 t0 to t, 2 times this. Okay, so this is good. This is good because, let me take the 2, let me take this 2 to the other side and write it as 1 over 2. So you see, this is what we had in this expression here. And if I now change the limits to upper limits to from t1 to t, so all the upper limits are t now, then I get the same thing, but I get 1 over 2 here, and which looks like becoming an exponential. Okay. Now let's look at the this term, third term, or rather I will look at a general term. So let's look at the nth term now. Okay. So now instead of having just t1, t2, I will be integrating over t1, t2 and t3 and t4 and t5. So you are going to be in basically n-dimensional t space. Okay. So you have t1, t2, tn, and the volume element in this space is dt1 integral dt2 integral dt3 integral dtn, and all the integrals are from t0 to t. Okay, just the same thing as before, but now for n dimensions. Okay. Now what I want to do is, I want to divide this volume, which n-dimensional volume, in similar fashion. And remember, what was the way in which we divided? We divided into independent volume elements without any overlap, and those volume elements were specified by saying that T1 is always greater than T2, and here other way around. Okay. So the same thing we will do. So we will divide this entire volume n-dimensional cube into distinct volume elements without any overlap using the same criteria. Okay. So how many are there? It depends on how many divisions we can make. So if I am given these times, okay, then I can have the following divisions. So I make some boxes here, and I say that this time is less than this one, this time is less than this one, and so forth. Okay. So the first one, I could have any of the n times from t1 to tn. So there are n possibilities here. Okay. So n possibilities. So let's say I put t in here. Suppose I made that choice, and now I have only n minus 1 choices, and I can make those n minus 1 choices together with these n choices. Okay. And I can fill up till I end up with one choice. So you see that I have in total n factorial choices, meaning I can divide this entire n-dimensional volume into n factorial smaller volumes, which will not have any overlap with each other, and together they will fill up the entire n-dimensional this n-dimensional cube, okay, which has side from t0 to t, length is t0 to t. Okay, so we see that we have n factorial such choices or such spaces. So let me write it down. So we have n factorial divisions of n-dimensional cube. Okay, in the T space. Okay, and if I sum all these n factorial regions, then you get the full volume element, full volume of the cube. Okay, so that's good. Now if I argue as before, the argument I gave here, right? Now you have instead of these two, a total of n factorial terms. Okay, and you can of course again rechange the labels and use the fact that time ordering will take care of everything irrespective of what arguments the edges have, and using that same logic you arrive at the following result, that maybe I should write on the next sheet, that integral t naught to t. So I am now integrating over the full cube, and I should take h of t1, h of okay. This entire thing, if I divide by 1 over n factorial, so if I take one part of it, okay, one division of this entire volume, then that is the one which is equal to this one. Okay, and this one dtn minus 1, this one will go from t naught to tn minus 2 and so forth, and this goes to dt2 t naught to t1, and this one will be dt1 t naught to t. Okay, so now you see I have changed the upper arguments to t and I have got 1 over n factorial. So now if I take this result, okay, and substitute in our original expression that we had got in here, okay, then you see I will have 1 plus, this one is fine, minus I times this, and this one will become minus I square over 2 factorial times, here it will be t, here it will be t, and this will remain the same, and similarly here I will have minus I cube over 3 factorial, and all the upper limits in this case will be t, and the same thing, and this is what I will write as the following. So I write that my result is this. It is maybe this is the last sheet, so I will write it explicitly. From t naught to t. Okay, and this I define to be the following. I write it as exponential minus I, okay, slightly differently, dt prime I have just brought in minus I here, and integration is from t naught to t, okay, and then I put a t here, time ordering operator here. So this t tells me that when I am expanding the exponential above, okay, and I should always ensure that the time the operators hi's, okay, are correctly time ordered. Okay. So this is the definition of this object. So what is the meaning of this object? The meaning of this object is the above expression. Okay. So that's just a convenient way of writing this bigger expression. Okay. So you see that we have succeeded at least in expressing the field phi in terms of phi i's only, okay, or phi i's and pi i's. if our HI included pi I, but for our Phi-4 theory there is only phi I. So you see here, now once I have found the solution of U like this, and you know HI is made out of phi I, so for our case HI is d4x, no, d cube x, phi x to the fourth, okay, and of course lambda over 4 factorial. Okay, so this is HI for us. So you see this entire U is constructed out of only phi i's, okay, because once you expand this will contain only phi i's, powers of it, which means that I have now expressed phi in terms of phi i's only, okay, which is one thing I wanted to do, okay. So that is good, and the reason why I wanted to do was because phi I evolves with free field, free Hamiltonian. So this will be very useful. Now what I should do next is worry about our ground state, okay, and do something here so that that also involves only objects which evolve in time with free fields, okay, evolve in time with free Hamiltonian. Okay, so good, we'll stop here and we'll meet in the next video.